Hi, my name is Miloš and welcome to Element 14 Presents. About a year ago, I made this robot arm right here and it got really popular. A lot of you guys loved it a lot, but I think it's time to make a new, better one. The main problem with this one was that these motors were just too weak for it. So I'm going to use bigger motors, these motors right here, to make a bigger and stronger one, but keep with the same idea of making it as cheap as possible. Let's make another arm. Before we get into the new arm, I'm gonna answer some of the most asked questions from the last video. The first one being is, why did I use these with these, when these have internal potentiometers? Well, that's the thing. On most servo motors, the potentiometers are internal and we don't have access to them, and I didn't wanna modify the servo motors in any way. And the potentiometer costs like 10 cents at this point. So I just use them as an additional axis and as a way for me to have an actual position feedback, which I can record with my microcontroller and then play it back using a Python script later on. So that would be the first question and answered. And the second one is, why use servo motors and not stepper motors? So here's the thing. The servo motor has everything built in, the controller, the gearbox, the everything. All you need to do is send it a PWM and it works. For the stepper motor to do the exact same thing, you need a stepper motor, either like this and then have bells, stuff like that, or with a gearbox, which adds to the cost. You need to have a separate driver, and you also need to have some kind of encoder if you want to have a closed loop driver and be sure that the motor is not skipping steps. All of that adds complexity, or adds a lot to the price as well, and my goal with these robot arms is to make them as cheap as possible. So that's the main reason why I went with the servo motors, and I'm doing it again this time. I'll for sure make one with stepper motors as well, but since I'm trying to make this one as cheap as possible, we're sticking with the servo motors. So let's see what I'll do differently this time compared to the last arm. This is the drawing I made for the last robot arm. On the left, you can see the configuration of the brachio arm that I wanted to replicate last time and that I want to replicate this time too. So last time we wanted the same configuration, smaller servos and position feedback for each joint. Last time I did that with potentiometer. This time, however, we're gonna do things a little bit differently. We still want the same configuration, but we want to go with bigger servos because those servos were too underpowered. So same size servo motors as on the brachio. We're gonna use bearings instead of marbles that we used last time. We're also gonna use bearings for each of the joints. And we're gonna use the DF Robot servo motors, which already have analog feedback built in. So to summarize, compared to the last arm, we will have bigger servos and we will use bearings instead of marbles. And each joint will actually have bearings instead of just the first and the last one. Let's take a look at the electronics now. Before we get to testing, we first need to, of course, finish the electronics. Here is the schematics I will be using. So all of the electronics will be based around the Raspberry Pi Pico, and the main purpose of it, as you can probably tell, is to control servo motors. So for that, we're gonna use these pins for the PWM. So these motors are special, as you've seen, because they also have a sensor pin on each one of them, and that's an analog feedback pin which gives you the angle of that motor. To read the 6 or 7 or however many motors you want using the Pico, we need some kind of a multiplexer, so I'll be using this one because it's locally available. The problem with it though is that it needs 5-volt logic and doesn't work with 3.3 volt logic. So I did 3 optocouplers to actually just shift that level so I can control it. And for me to be able to cut the power to the motors, I added a small relay, which is also triggered by a small optocoupler because it's a pretty beefy relay which can carry a lot of amps. So that's everything when it comes to schematics. There's not a lot of electronics in this one. Let's now get to actually see how this looks assembled and finally test it with some servo motors. Before we actually get to testing of the controller, first we need to, of course, program the Raspberry Pi Pico. This is the code I split into a few tabs for easy organization. The first tab contains the library, the pins, all of the parameters I will be using and the variables, of course. So the main thing I want to point out with the code is that I'm using timers. I use it so I can have multiple processes run in parallel. They are defined in the setup function here. This is an example of that timer, and what it essentially does is every this amount of microseconds it calls a handler function, which is like an interrupt function that you shouldn't do anything big in it, like print anything on serial, but you can change some flags and then handle those flags in the loop, for example. And this is how you can get a really good performance out of the Pico. This is what I've done here. Here we have, this is just one big function called decode serial messages. It's a little bit messed up because I zoomed in a bit too much. Here now you can see it better. It handles all of the commands that are in the G-code format. For example, C11 turns on the relay while C10 turns it off and stuff like that. And we have the C6 command where you send it 6 angles and the robot goes to that position. Here we just have the functions that are needed for everything else. So that's pretty much the whole code. Let's take a look at the controller now. Here we can take a look at the electronics that I've shown you, but in real life. Here is the Pico, so that's the main thing that we have for this controller. We have the relay and the circuitry for the relay here, like the small op-amp that you can see here. I had a bunch of big capacitors that I had lying around just to keep everything stable, and the rest are pretty much just connectors to connect everything. For example, here at the end there's a whole perf board with just connectors so that it's all nice and tidy with the least amount of wires as possible. One thing I had to do and still have to solder is this little thing here. So these are the 3 optocouplers on the breadboard. My original idea was to use a small breakout board that's a level shifter, but because it didn't work as expected, I made my own with 3 optocouplers. I also added this connector here, which breaks the path of activating the relay, which is connected to this, which is a safety switch. So if a robot hits something that you don't want to hit, you can just press this and the power will be cut off from the motor. Let's deactivate it, and I've connected the single servo. Now you will see on your screen the serial monitor. So let's first send a command to turn on the relay. If you listen closely, you can hear it switch. It's on. You can see the measured voltage from the power supply. We need to turn the PWM on to enable it. And now we can send the command to the motor, for example, 90 degrees or minus 90 degrees, where of course the 0 would be its central position. But these motors are special because they can go plus 135 and minus 135. So that would be all of the electronics tested. Let's move forward now with the design of the actual robot arm. Time to look at the CAD model for the robot arm. This down here is the frame for the robot arm. You can make it out of whatever you want. I will be making it out of extrusions. That's something that's not important. Let's take a look at the main arm itself. So we have these 3 joints here. We have one joint on the top and one joint at the bottom, as I've shown before. And my idea was for this big joint to have to use a big style bearing so that cables can pass through. But of course those bearings are expensive, and with the goal being to make the robot arm as cheap as possible, let's take a look at how this bearing actually works. So this is the whole bearing. If we take off this cover here, we can see that inside there is a small run, and this central part here runs on 6 small wheels, which are usually used for 3D printers. And like that, it can pretty nicely handle any kind of loads that are not straight on the axis, and it spins freely. I didn't have any problems with it. And also, if you tweak to get these tolerances right here, it won't bind and there won't be much play in the robot arm either. So that's for that joint. As for other joints, the only main thing to say is this. Let me just take this servo cover off. So the servo motor is sandwiched here. That's all you need for a joint pretty much. And the servo horn attaches to this servo arm. But on the other side, to make the arm more stable, there is a small bearing which you can get. You'll have the full part list as well as all of the CAD files free to download down below, so that the joint is supported on both sides, and this makes the robot arm much more sturdier. And since I will be using bearings here, it's much better than the one on the Arduino arm where it's just plastic on plastic. Another thing to mention is that on the top, let me isolate that joint. We have I did a similar thing as we did on the bottom joint. If you take a look here, we have this central piece that's mounted on the servo, and I wanted to make it a bit stronger. So I added, let me just find them. I added a few bearings so that it's supported as well. Let me just get rid of this. And this, here we go. So these bearings are actually running on in this run here, and that's what's keeping the whole motor stable and not having the motor bearings inside are not being pushed to the limit, so it won't fail and it will last longer. That's the whole CAD model. Now I'll show you a quick time lapse because I don't want to make you go through a 1 hour assembly. And the robot arm is done. I'm really thrilled with how it turned out. The big bearing is incredibly stable, as well as the one on top. The one on top is a bit heavier, but the motors are strong enough to withstand the torque. And I just love the clean white design, the aesthetic of the whole arm, and with all of the organically looking shapes. So I made this stand out of 2020 aluminum for it, and added this LCD drawing tablet for it so we can do some stuff with the robot arm. Let's get to the actual fun part of testing this arm now. It's finally time to test out the arm. So the arm is turned off now. Let's turn on the relay, hear the click, and let's send it to the safe position, which is all in zeros. This is the only fast move, because for the other moves I programmed it to actually have a ramp so it doesn't go as fast. So for example, here is me moving just the first axis. You can see that it moves slowly. It doesn't just jump to the position. Let's center it again. Let's move it to something like this now. And we can switch it back again. For this, you can see how the top stays, how the top part stays always parallel. So it doesn't change, so that means that the motors are pretty well synchronized. We don't have direct control over that, but for what it is, it's pretty good. You can also see that if we do something like this, if we move the first and the last joint in counterclock in different orientations, that will be the same. Sorry, because and you can see the pen at the top staying completely still. This you need to give them the same angle because there's a gear in the bottom, so the direction is switched. But yeah, that's it. All of the fundamentals work really nicely here. You can control all of the angles for the robot. Now let's make it a bit better by actually writing some scripts in Python for controlling the arm. Now that the base test is done, let's do some more advanced stuff like the calibration. So the motors are never the same, and there are differences between the motors when they return, what voltage they return based on their position, and we need to record all of that. For that reason, I wrote this Python script to do that. It essentially just sends commands to the robot to go into a few specific positions, as you can see here, like the 0, 0 position, and it wants to test all of the motors at -90 and 90 angles. It gathers all of those positions. It gets the median value out of the 1,000 positions, so we can get accurate measurements. And in the end, it calculates the parameters that we need, and it stores them in a CSV file, as you can see down here. Okay, so I'll run this code now, and on the part of the screen you can see what the robot arm is doing. You can hear the relay. So this is the 0 position, and now it will be in this position for 10 seconds to record the data. After that it will move to a different position, and then to another one, and then back to 0 again. I'll speed up the process between the positions so you don't have to look at everything for 10 seconds. And the calibration process is complete. As you can see by the printout down here, you can see all of the parameters like the middle position, maximum position, the calculated delta, and calculated coefficient array. I'm sending the raw ADC readings from the Pico to the PC to not use up the resources on the MCU, and I'm converting that to angles in Python, and these are the actual parameters I'm using to do that we've just calculated. So now that you've seen this part, let's see how it works when we want to record some kind of movement with the arm and then play it back. This is the next script I will be using. This one is mainly for recording all of the angles. Here you can see the load calibration parameters function. This loads the parameters we just recorded. It pretty much just waits for the data coming from the MCU, and it just converts those angles, those raw ADC readings to angles, and stores them in the CSV file, which we will later play on. So for example, here I've put the recording session to 30 seconds. So I will turn on this script and move the arm around a bit so we can see the playback later. And we're trying to get all of the angles to move. And okay, that would be 30 seconds. We now have a saved file. Now I'll switch to going to a different script, as you will see that will just use that file that we just recorded. Okay, so this is the file in the directory that I want. This is what we've just recorded. And now if we click here, hear the relay, it goes to 0. And now the arm will try and follow the position that we gave it in the recording. And though that scraping there is why we have the emergency switch for cases like that. Another thing to mention here is that you can see how jittery the arm is, and that's because the signal is unfiltered. and I'll show you what kind of a difference filtering makes in the next clip after this playback is done. And the playback is done. And you heard the relay go off. Let's now go to Google Collaboratory, check the data that we just recorded, and see if it actually needs some filtering. Okay, we're in Google Collaboratory now. This is what I used for plotting out for any data that I have for testing out stuff in Python, like that, because I can use it either from my iPad or my laptop. Here we have the data that we've just recorded and we want to filter it, but before we do that, let's see how this data actually looks. If you see parts of the signal here or here, you can see how noisy it is, and that's what we're actually trying to filter out. Here's just a part of one of the signals, and you can just see the noise up here, and that's all of that jittering that we've just seen. And this is what we can get with some basic low-pass filtering. These are the differences. Of course, the signal is not the same after this, but for something like this, this is completely acceptable. Of course, for anything more high precision, this would be anything but good. Here is how that looks for the whole signal, and this is how all of that looks for all of the signals at once. We can also, of course, change the parameters of the filtering to get it as we like, but this is just something that I wanted to try to see if it will make the movements a bit better. Let's now go back to our player script and play the new data recording 49, but this time filtered. Okay, so now we have the data recording 49 but filtered instead of just the regular file. So let's play this and see how it compares, if it's gonna be jittery like the file before. You can see the movements are a bit smoother. It's still hitting the LCD, but you can see that even though it jitters a bit, it's much better than last time. I'll put a side-by-side comparison after this so we can see how it looks. But yeah, filtering the signals is something definitely that should be experimented with further. Maybe just not to this big of a degree like I've done here, but it for sure helps if you just want better, more fluid movements. And we have back to the safe position quickly. Now let's look at the comparison between the filtered and unfiltered. Here we have a side-by-side comparison. So on the left is the unfiltered signal for the robot arm, and on the right is the filtered one. What we want to look at here is the shaking of the robot arm, especially in some static positions, and you can see a lot of improvement there. There's still a bit of jitters here and there, but that's also a lot to the servo motors themselves with their internal control loop, and just the fact that for position feedback they're using potentiometers and not encoders, which are just not reliable for a task like this, where you want accuracy to be in a sub 1 degree range. But still, they are pretty cheap and they get the job done. We did end up with a functioning small robot arm that we can experiment and play with. Thanks so much for watching. Hope you liked how this robot turned out. If you have any questions or comments about this robot arm, please leave them down below or on Element 14 community. What do you want to see next? Do you want to see me connect this arm to the robot operating system and show you how that works and do some direct and inverse kinematics? Or do you maybe want to see another robot arm, but this time with stepper motors? Let me know down below. Until next time, see ya!